One of the consequences of similar triangles is something that we often call the triangle proportionality theorem. Now, when we have similar triangles, the proportional relationship between the sides requires that we use the entire side of the triangle. And what the triangle proportionality theorem allows us to do is talk about the relationship between segments of a side of a triangle when two sides are cut by a line parallel to the third side. So the full statement of the triangle proportionality theorem says that when a line parallel to a side of a triangle intersects the other two sides, it divides those sides proportionally. In this case, what we're talking about is that the line xy is parallel to the line containing A and C. Therefore, the sides AB and BC are cut proportionally by the line containing xy, or that BX over AX is the same as BY over CY. Go ahead, pause the video, copy down the statement of the triangle proportionality theorem as well as the diagram and the ratio that results from it. Come back when you're ready to hear a little bit more about it and then go through a proof of it. So, as you might have guessed, the proof of the triangle proportionality theorem is going to rely on similar triangles as well as the properties of ratios and proportions. So in order to do that, let's go ahead and shrink that down here. We're going to start with the only thing that we need to be given here, which is that xy is parallel to AC. That is the given. That is the only thing we need to know, that xy is parallel to AC in triangle ABC. Well, now that we know that, we have parallel lines and we have some transversals, so therefore we have some congruent angles based on the corresponding angles theorem. Angle A and angle BXY, as well as angle C and angle BYX. So let's go ahead and mark that down in our proof. Angle A is congruent to angle BXY, and angle C is congruent to angle BYX. That's all because of the corresponding angles theorem. That tells us that when transversals cut two parallel lines, corresponding angles are congruent. Now, thinking back to triangle similarity, we have two triangles, BXY and BAC, that have two congruent angles. Therefore, by the angle-angle similarity postulate, which we can just abbreviate as AA there, we know that triangle BXY is similar to triangle BAC. All right, so now as a part of the triangle proportionality theorem, we have gotten to the step in the proof where we have two similar triangles. Well, when we have two similar triangles, one of the most useful things we can do is talk about what sides in those triangles are proportional. So in the case of these two triangles, we know that the ratio of BA to BX is the same as the ratio of BC to BY. We know that because those triangles are similar and corresponding parts of similar triangles are proportional. CPSTP as opposed to CPCTC from congruent triangles. Okay, well now we are partway there. Remember that the triangle proportionality theorem said that the ratio of BX to AX is the same as the ratio of BY to CY. So what we're really after in terms of the proof here, we're going to flip those ratios upside down and say that AX to BX is the same as the ratio of CY to BY. And why are we going to reverse the ratio and the proportion as we had it before? Well, because with the corresponding parts of similar triangles being proportional, we already have denominators of BX and BY, and we can just flip a proportion vertically as long as both fractions are reciprocated, and the proportion still holds. So we are partway there now. We've got our similar triangles, we've got BX and BY, and now we're going to do a little substitution using things that we've known before. BA as a segment is made up of AX and BX. So therefore, we can substitute in AX plus BX over BX is equal to a similar type of substitution for BC, being that by plus cy is the same as bc, and that is just by basic substitution. I'm not going to write it in the reasons over there for space reasons, but now we have the proportion ax plus bx over bx is equal to by plus cy over by. One of the properties of proportions that we saw before is that if we have two values being summed in the numerator and one of those values is the same in the denominator, that we can essentially cancel out those values, and we saw the proof of that when we were talking about the properties of proportions. So here we have a bx and a bx, and a cy, a by, and a by. So those effectively cancel out. Those ratios are equivalent to ax over bx being equal to cy over by, because this is a property of proportions. So there we go. That is the proof of the triangle proportionality theorem. Now, anytime you see nested triangles like this, you can talk about the relationship between the similar triangles created by the parallel lines, BA and BX, or BC and BY, or you can go directly to the point of comparing the proportional lengths BX and AX to BY and CY, which is something that we weren't quite able to do before. Again, the triangle proportionality theorem says that when a line parallel to a side of a triangle intersects the other two sides, it divides those sides proportionally. Namely, that BX over AX is equal to BY over CY.